First, I would like to thank Computex for giving me this opportunity to introduce what is compound semiconductors and how compound semiconductors can shape our future lives. 3-5 compound semiconductors consist at least one element from group 3 in the periodic table and one element from group 5. They chemically react with each other and forming a compound. Gallium arsenide is the most representative compound semiconductor. Gallium nitride is the other. Indium phosphide is another one. And these are the three basic compound semiconductor materials. For integrated circuit applications, compound semiconductors has the advantage as high speed. It can run theoretically 5 to 6 times faster than silicon's counterpart. The second advantage of using compound semiconductor is that for most of them, they are able to emit lights, which silicon cannot. And they also absorb light more efficiently than silicon. And it provides a very wide frequency wavelength spectrums from infrared, visible light, all the way to UV light. Depending on the applications you design for, you can carefully choose the right material and the concentration of each element for the wavelengths you designed for. Okay, and actually compound semiconductors is around our daily life. For example, in smartphone, compound semiconductors is inside as the power amplifier to transmit very fast and complicated signals to the base station. And also the Wi-Fi router has a compound semiconductor parts, and inside the optical fibers, compound semiconductor act as the light emitting source and interface IC. And also in display, compound semiconductor act as the backlighting. And the compound semiconductors are also in satellite, base station, and radar. Next, I'm going to take a few minutes to give you an overview on the key milestones which has been achieved by compound semiconductor in the past. Starting from the first transistor, which was invented in 1940s at Bell Laboratories by these three very famous scientists. The first transistor was germanium-based. It's not silicon, it's not compound semiconductor either. In 1960s, the first LED was demonstrated using gallium arsenide for red LED. And the early 3-5 transistor was actively developed and materialized between 1960 to 1980s. MACFET was the first, the initial 3-5 transistor, which later on evolved into PHEM, which is used for today's high frequency, for example, in millimeter wave or microwave integrated circuits. HBT is the kind of a bipolar transistor which is used in today's smartphone power amplifiers. Okay, and the first vertical cavity surface emitting lasers was invented in 1980s by Professor Iga, and VCSEL now is used as the light source for data communication, and it also has been widely used as a 3D sensing device. Believe it or not, gallium arsenide has supercomputer between late 1980s to 1990s. It demonstrates processing speed around 3 times faster than silicon, and the project was not successful. partly because it consumes too much power. The first blue LED was demonstrated in 1990s. This was a very important milestone because by then all the three primary colors of light becomes available: red, green, and blue. And essentially all the colors becomes available for display. And based on the same technology foundation, white light LED becomes later developed and rapidly replace existing traditional light, which save enormous amount of energy for the world. Mobile phone was the first consumer product which brought gallium arsenide IC into true volume production. And even now, we estimate still around 50% of gallium arsenide ICs was used for smartphone. Compound semiconductors are widely used in satellite communication in both space and the ground terminals for transmitting and receiving signal purpose. Compound semiconductors certainly help to make satellite commercialized possible. In 2017, iPhone for the first time introduced Face ID product using VCSEL as the light source for 3D sensing device. And this was the first time in the world gallium arsenide VCSEL was in true volume production on 6-inch gallium arsenide wafer at Win Semiconductors. 5G smartphone contains a lot more compound semiconductor contents simply because there are newly created frequency band for 5G and therefore needs a more gallium arsenide power amplifier inside per phone. This year, Mini LED was introduced as the backlighting for flagship tablet as the display. This certainly brings the display technology to the next level. We believe in the coming few years, maybe micro LED will come out and further advance the display technology. It's worth to mention that today, the world's fastest transistor is done by compound semiconductor with frequency response greater than 1 terahertz, which is 1,000 gigahertz, incredibly fast. Next, let's watch a short video on how future life might look like.
Wireless communications connect our lives at increasing speed. Compound semiconductors enable wireless connectivity and make possible a new generation of image sensing. It not only contributes to the rapid evolution of society, but also expands the public's vision of the future. Technology evolves to provide a more productive lifestyle and benefits from the advantage of compound semiconductors.
Okay, from the video, we see the ubiquitous access of internet has become a lifestyle. We expect to live in a safer and a more secure life with environmental friendly green energies. This lifestyle translates into enabling technologies which must be able to provide seamless connectivity and smart sensing devices to keep our life safe and secured. We also need power-efficient devices to be environmental friendly. Let's see how compound semiconductors are able to contribute on each aspect. Starting from smart sensing devices. There are 3 types light sources for 3D sensing technology: LED, VCSEL, and edge-emitting lasers. Each has their own advantages over the other 2. VCSEL is the most widely used light source today, however. There are two depth sensing methods, structured light and the time of flight. Time of flight is more intuitive by measuring the flying time and the phase shift of reflected light to determine the distance. As to structured light, what it does is to project a predefined dot patterns onto the object. By measuring the patterns, distortion, and through the complicated calculations, we are able to determine the object's 3D profile pretty accurately. 3D sensing technology is used for facial recognitions in situations that high security authentication is required, such as mobile payment, unmanned store payment, home and office access. It can also be used to monitor and control traffic or crime prevention purpose in smart city scenario. Besides facial recognition, other biometric applications such as heart rate and blood oxygen level detection on wearable devices becomes very useful to monitor personal health condition. And eye tracking and under-screen fingerprint are another two examples among many others. AR is an emerging application for 3D sensing. It helps to provide a better immersive experience for AR. It has been used in shopping, entertainment, education, training, and medical treatment. And it is expected to be adopted by wearable devices in the future. Automotive is probably the most attractive application for 3D sensing technology. LiDAR is a kind of 3D sensing devices for automobile to assist the driver for safe navigation and collision avoidance. Ultimately, we believe LiDAR will be used in autonomous car in years to come. The initial use cases include unmanned last mile delivery and robot taxi, self-driving bus, and the picture in the center shows the Taiwan's first self-driving bus launched this year, running on normal road in daytime. And the driver monitoring system, DMS, provides a real-time evaluation of the driver's status to ensure the driver is in a good condition for driving by detecting, for example, if the driver's eyes are closed or if the driver is falling asleep by nodding his head and provide a warning to the driver. 3D sensing devices serve as a function of machines and robots' eyes. It helps to provide rapid and accurate positional information for robots, which makes factory automation a lot more efficient and largely increase productivity. Now we switch gear to the second aspect, power and efficiency. During the course of advanced technology to improve humans' life, frequently it consumes more energy when using new technology. However, which contradicts to the green energy vision. Let's see how compound semiconductors can help to address this dilemma. Gallium nitride and the silicon carbides are a class of compound semiconductors with so-called wide bandgap semiconductor, which has unique material properties for high power and high efficiency applications due to their high breakdown field, which makes them ideal for high voltage and high power applications. Silicon carbide has extremely good thermal conductivity, which is helpful to dissipate generated heat during operation. Therefore, power efficiency can be greatly improved using silicon carbide. High electron velocity makes both gallium nitride and silicon carbide ideal materials for high frequency and fast switching power applications. It greatly reduces the energy loss during power conversion. This page shows the applications for gallium nitride and silicon carbide. For power conversion applications, both gallium nitride and silicon carbide have been adopted in electrical cars, data center servers, and fast charging adapters. Gallium nitride devices are used for 5G base station, power amplifiers, communication satellite, and even defense applications. Refrigerators, air conditioners, TV, and illuminations are the top 4 most energy-consuming household appliances. Collectively, they consume around 50% of household electricity. Compound semiconductor devices help to greatly reduce energy loss. For example, using compound semiconductor power inverters, the energy loss can be reduced more than 80% for refrigerators and air conditioners. LED is able to reduce the electricity consumption if used as the backlight for TV and to replace conventional incandescent lamps. Together with electrical vehicle and the data center, etc. applications, using compound semiconductor devices is able to save tens of nuclear power plants worldwide. This is an incredible amount of energy being saved. Okay, this diagram shows output power versus operating frequency plot for various power conversion applications. For highest power applications, silicon carbide is the technology of choice. As for high operating frequency applications, then gallium nitride is the best candidate. Electrical vehicle falls in the middle between silicon carbide and gallium nitride. Currently, silicon carbide is still the dominating technology. Gallium nitride could catch up in the future when technology becomes more mature. Okay. There are still many technology challenges for gallium nitride, ranging from substrate to epitaxial material processing, reliability, to packaging. Due to limited time, we are not going into detail on each here. The third aspect is ubiquitous internet access. Ubiquitous internet access has become a vision and a must for modern lifestyle. We want to be able to access internet anytime, anywhere. And compound semiconductors can certainly help to realize this vision. This page shows examples that compound semiconductor devices are used in all the networks pervasively, including satellite internet access, 5G optical access, and the 5G radio access. Where compound semiconductor has its role in the forms of high-frequency amplifier, low-noise amplifier, light-emitting source, light-receiving device, and the photonics integrated circuits. 5G is becoming the network to connect everyone and everything. It contains 3 important features. The first one is high reliability with low latency. Enhanced mobile broadband is the second, and massive IoT is the third. In terms of frequency spectrum, 5G needs a millimeter wave frequency, which is around 30 gigahertz or above to provide large bandwidth for high data rate transmission. However, the coverage is very limited. At the same time, 5G also needs lower frequency bands, which we refer as sub-6 gigahertz, to support wide coverage. Both millimeter wave and sub-6 gigahertz are required to make a 5G network complete. This page shows several 5G use cases where the features described in the last slide are required. For example, in a sports stadium powered by 5G networks, many cameras can be installed around the stadium. No matter where you sit, you are able to see any player from any angle with a high fidelity image real time. This is every seat is the best seat user experience. The user experience can be further enriched by merging with the AR and the VR technology. And the V2X is a good example to use all the 5G features, low latency, high capacity, and the machine-to-machine type of communications. Through vehicle-to-vehicle communication, our own car can see using the surrounding vehicle as its own eyes. Telemedicine is another 5G use case, for example. How to increase data transmission capacity? We can certainly use a higher order modulation signal to increase the bits per second, and using higher frequency as a spectrum where a much wider bandwidth is available. And multiple access techniques can effectively to multiply data transmission capacity. And installing more small base station is able to increase the network capacity per area. This is another approach. Previous page shows the system-level approaches to increase data transmission capacity. But down to semiconductor device level, the challenges are translated into high-performance transistor technology is required in order to operate at high frequency. Higher linearity performance is required to amplify higher order modulation signal, and the higher operating voltage is needed to transmit more power for longer range. And improved power efficiency is constantly required to reduce power consumption, particularly for power amplifier. This slide provides a plot of output power versus operating frequency for RF applications for various device technology and the associated applications. There's no one single technology is good for every applications. Therefore, right device technology has to be carefully chosen for the targeted application. High frequency and high power are of different challenges. The greatest challenge is for application toward the upper right corner of the chart. Compound semiconductor device technology is the best solution in this category. Okay. It is believed the future life will be connected by massive intelligent devices through the fusion of 6G, Super IoT, and AI to achieve the ubiquitous AI access as the vision. In addition, the boundary between real and the digital world is getting blurred. For example, 3D hologram potentially can be the next generation display technology and the user interface. It can be further merged with the ideal so-called digital twin that we are able to real-time interact, for example, with our colleagues, with our friends and families, as they're personally in front of you without constraint by space. This is like sci-fi movie or a Star Trek scene in real life. Telesurgery with hologram user interface is another use case example. There are many other proposed by companies, universities, and organizations as potential 6G services. All of these new services require extremely high data transmission connectivity and a massive amount of smart sensor devices, as well as a supercomputing power seamlessly integrated together to achieve the goal. Moving towards 6G, according to Cisco's VINI index, global mobile data traffic grew at a compound annual growth rate of 46% in the past 5 years. If we extrapolate using the same rate, 10 years from now, the mobile data traffic will be 44 times of today's data traffic. This implied an unprecedented stringent performance requirement is needed for next generation network. For example, in order to achieve the hologram display user interface mentioned in the previous slide, it needs probably greater than 100 gigabit per second ultra-fast data transmission electronics to realize. Therefore, sub-terahertz device might be needed to provide sufficient bandwidth. In conclusion, we have shown compound semiconductors played a pivotal role to drive innovations to advance our future life. It is believed we are still in an initial stage for another disruptive growth on compound semiconductors. This is driven by innovative emerging applications which require enormous frequency bandwidth and high-performance smart sensors. These are exactly the strengths of compound semiconductor, and it is expected compound semiconductor is going to play an increasingly important role in our future life. Thank you.